An interstellar comet, older than most stars, is passing through our solar system. Its trajectory points to an origin in the 10-billion-year-old thick disk of the Milky Way. This is Tracy Atlas. It's releasing 8 times more carbon dioxide than water, yet its trajectory barely shifts. Chemistry screams activity, but motion reveals no thrust. How could this ancient time capsule maintain its pristine ices for eons? An interstellar comet, older than most stars we see today, may be passing, and it doesn't behave like any comet we know. Initial tracking places 3I Atlas in the Milky Way's thick disk, a population about 10 billion years old. We'll break down the evidence behind that age estimate, why its carbon dioxide-rich chemistry matters, and how such an ancient object could have avoided starlight long enough to maintain its pristine ices. Keep watching to discover what this time capsule can reveal about conditions in the early galaxy and what would be considered a true red flag for something artificial. Why does its trajectory point to an ancient origin? A comet moving too fast to be retained by the sun points to a much older history. The question is, how do we trace that path through space and time with enough confidence to say it began billions of years ago? It starts with the trajectory's shape. Hyperbolic orbit means the object isn't bound to the sun. In simple terms, orbital eccentricity measures how elongated an orbit is. Values above 1 are not bound. For 3 in Atlas, initial solutions yielded an eccentricity above 6, which is extreme. The first alert from the Asteroid Terrestrial Impact Last Alert System in July 2025 triggered rapid follow-up. Dozens of telescopes collected position measurements night after night to refine the trajectory. Each new datum reduced error margins and narrowed the range of possible orbits. You might ask if an error could simulate that velocity and shape. That's the right test. Most long-period comets come from the Oort cloud and have eccentricity near 1 barely bound. Interstellar objects are rare, so the burden of proof is high. Astronomers respond by doing astrometry, which is careful measurement of an object's position compared to background stars. Fit the complete set over many nights, and the math leaves room for a bound or unbound trajectory. Here, the best-fit solutions stayed well above 1, even when analysts allowed for measurement noise and outgassing effects. That makes a bound orbit an unlikely hypothesis. Entry velocity adds another constraint. Measured velocity relative to the Sun was approximately 58 km per second, which is well above what solar system comets show far from the Sun. High velocity matters because planetary gravity can bend a trajectory but cannot create energy from nothing. If you enter so fast on an already hyperbolic trajectory, you're unbound long before entering the heliosphere. Once the orbit is secured, researchers place the trajectory in the galaxy. They run backward models that include the Sun's motion, Milky Way rotation, and nearby star gravity. These models produce an entry vector, which is the direction and velocity with which 3I Atlas approached before the Sun significantly altered its course. That entry vector aligns with thick disk kinematics, a major component of our galaxy composed of older stars with higher random velocities. Let's define the thick disk in simple terms. The Milky Way has a thin disk where the Sun lives and a thicker, fluffier layer above and below it. The thick disk contains stars that formed approximately 10 billion years ago, moving with greater velocity dispersion and showing different chemical patterns like lower metal content. A link between a comet-like body and thick disk kinematics is unusual because typical comets trace back to the Sun's thin disk neighborhood and the cloud that shares the thin disk's ordered rotation. Could something else push the orbit to appear interstellar? 2 alternatives arise. Is data systematics like calibration problems? The other is unmodeled gravitational tugs. Both are checked by comparing independent observatories, filters, and reduction processes. Agreement between sites and hyperbolic solution stability, after adding more nights of data, argues against those alternatives. That's why consensus opinion treats 3 and Atlas as a genuine interstellar visitor. Together, the path is not only unbound, it points back to an ancient, colder place of origin. An object moving at thick disk velocities likely formed in a system where ices could survive. Then it was expelled and remained largely intact in deep space for eons. That makes 3I Atlas a plausible 10-billion-year-old time capsule. If trajectory preserves its age, chemistry can tell us how ices stayed preserved in darkness between stars. A carbon dioxide-rich comet that refuses to move. JWST detects carbon dioxide emanating from 3I Atlas, approximately 8 times more CO2 than water, yet its trajectory stays almost perfectly on course. That combination raises a mechanical question. Outgassing, which is vapor escaping from heated ice, acts like small thrusters. In most comets, that's observed as non-gravitational acceleration, a small but measurable push that shifts the orbit beyond what gravity alone predicts. Here the thrust signal appears strong in spectra, but trajectory barely flinches. Let's rely on observations. Hubble images show a narrow teardrop-shaped coma, the diffuse envelope of gas and dust around the nucleus. That shape suggests organized flow, not chaotic scatter. Hot JWST infrared spectra add chemical breakdown. Carbon dioxide dominates, while water lines are weak at similar solar distances, where solar system comets switch to water-driven activity. In simple terms, a volatile we expect to evaporate early is doing the heavy lifting. If so, we should see thrust, we don't. This discrepancy establishes two main hypotheses. One is a mass and density solution. If the nucleus is larger or more compact than expected, the same gas thrust would produce lower acceleration. The other is a geometry and distribution solution. If vents are distributed across the surface, or if the active area behaves symmetrically, forces can cancel and hide any net thrust. Both ideas can match parts of the data. Neither is confirmed. Here's density context. Typical comet density clusters around 1 gram per cubic cm, roughly half water's density. That reflects a porous icy interior with voids. Metal-like density would be extraordinary. It would imply composition or structure resembling an iron-rich rock more than a fluffy comet. Consensus is such high density is an unlikely hypothesis without strong size constraints and independent mass estimates. We don't have those yet. Some have proposed an artificial origin hypothesis, citing reports of strange radio signals or claims about prime numbers. These claims remain unconfirmed. NASA has not verified artificial signal detections from 3I Atlas. For extraordinary claims, the standard is repeatability, evidence from multiple instruments with clear calibration and independent teams reproducing the result. Until that appears, general opinion favors natural explanations fitting known physics. A natural path starts with temperature and depth. CO2 sublimates transitions from ice to gas at lower temperatures than water ice. If 3I Atlas preserved deep cold layers, CO2 could vent first as sunlight penetrates insulating crust. If those vents are distributed around the surface, one jet can cancel another, leaving a bright coma, but little net thrust. Another working hypothesis is a larger, more compact nucleus than assumed. If size is even modestly greater, mass increases rapidly, and the same gas escape produces lower acceleration that could be below current detection limits. Polarization behavior adds a complication. Observers report an unusually deep narrow negative polarization branch in scattered light. That suggests of unknown structure or composition, doesn't require artificial materials, points to grains that formed in cold conditions and remained unaltered. What we still don't know is exact shape, spin state, and venting pattern. That matters because spin can average forces during rotation and shape can channel gas along shorter paths. If nucleus rotates with vents near opposite longitudes, thrust can cancel itself during each spin period. If coma includes extended sources, grains releasing carbon dioxide after takeoff, effective thrust can scatter and weaken. Cautious conclusion is simple. A carbon dioxide-rich, minimally processed interstellar comet can release gases strongly and still show little acceleration if forces balance or if nucleus is more massive than assumed. Artificial explanations are an unproven hypothesis. Next check comes soon. As 3I Atlas passes through perihelion and exits view briefly, monitoring will pause. Then it resumes with new geometry. If thrust pattern changes after closest approach or if delayed activity increases, we'll see which idea holds. Conclusion, here's the key. 3I Atlas behaves like an ancient carbon dioxide-dominated interstellar comet. Its strong carbon dioxide activity, alongside almost no measured outgassing thrust, points to cold materials from early galaxy that stayed stable for billions of years. That makes it a clean probe of how ices act at low temperatures. Watch the perihelion window and data that follows. Look for JWST spectra, Hubble images, and ESA observations that repeat results across instruments. treat bold claims as hypotheses until multiple teams reproduce them. The quiet surprise may be this, not alien engineering, but a clearer view of how the first icy worlds formed.